93 million people. That is how many human beings had their private data stolen through a single login box. In 2023, a ransomware crew called CompTIA found one flaw in a file transfer tool named MOVEit, and roughly 2,700 organizations fell in a matter of days. Here is the part that should keep every developer awake at night. The attackers never guessed a password and never phished an employee. They typed a few careful characters into a form field. The database did exactly what they asked, and there is a single defensive line of code that would have stopped every bit of it.
SQL injection is the name of that flaw. This is Professor Erica, and the definition the exam wants is precise. SQL injection is a code injection attack where an attacker smuggles malicious database commands into an input the application trusts. Tonight we go deep on Objectives 2.3 and 2.4, the web-based and injection sections you will be tested on.
Hey everyone, Elena here, and the exam loves to test whether you can tell the injection types apart. SQL injection targets the database, command injection targets the operating system shell, and cross-site scripting injects into the victim's browser. Same family, the smuggling of untrusted input, 3 different destinations.
I'm Michael, and I love this one because you can actually watch it happen. The root cause is a single mistake. The application takes whatever you type and pastes it directly into a SQL query as text. The database then receives one long string and cannot tell where the developer's instructions end and where your input begins.
And the viral version of this says you need elite hacking skills to pull it off. The honest verdict is the opposite. When input is glued into the query, the database cannot tell your data apart from its own code, and that single confusion is the entire attack.
It helps to take the database's point of view. It never sees a username box and a password box. It only ever receives one finished sentence of SQL. If you can sneak your own grammar into that sentence, the database obeys it as faithfully as it obeys the developer.
Let me draw the exact line this whole attack crosses, because once you see it, you cannot unsee it. In every query, there is a boundary between what is supposed to be data and what is supposed to be instructions. On the safe side, your type name is just data, a value the database stores and compares, never something it runs. On the broken side, that same type text crosses over and becomes instruction, part of the command the database obeys. It is parsed as code and the database runs it. Injection is nothing more than input jumping that one line, from a value to a command.
And before anyone files this under ancient history, injection still sits at A03 on the OWASP Top 10 today, the industry's list of the most critical web risks. It held the #1 spot for years. This is not a fringe bug. It is the one we have been warning about the longest, and it keeps landing.
MOVEit was not even the first headline. Back in 2008, a man named Albert Gonzalez used SQL injection to break into the payment processor Heartland and several retailers, stealing well over 100 million card numbers. He got 20 years. The technique that sent people to prison 15 years ago is the same one we are about to type tonight.
And MOVEit proves the stakes are not theoretical even now. Roughly 2,700 organizations and more than 93 million individuals, all flowing from one injectable field across thousands of servers. The vulnerability even has its own name in the official government catalog.
We can pull up that exact record right now. The National Vulnerability Database tracks it, and I want you to read one line for yourself. There is the entry CVE 2023-34362, and here is the part that matters. It sits inside the Known Exploited Vulnerabilities Catalog, which is the government's confirmed list of flaws being attacked in the wild. And the weakness type right there on the page reads improper neutralization of special elements used in an SQL command, weakness number 89. Stick with me, because that mouthful is just the formal name for everything we are about to do by hand in a live terminal.
Before we open that terminal, there is a question that shows up under almost every video on this attack, and I think it frames the whole episode. Erica, you have been sitting on a hand, so let me bring you in.
It is the perfect place to start. People ask, if SQL injection is so old and so famous, why did it still break MOVEit in 2023? Hold that thought, because the honest answer is the reason this episode exists.
The answer is uncomfortable. The fix has been known for 2 decades, but real software is millions of lines deep, written by hundreds of hands over many years. It only takes one forgotten query, one legacy module nobody dared touch for the whole castle to fall.
It was exactly that. A mature, widely trusted product used by banks and governments, and the flaw lived in a quiet corner that had handled file transfers for years. Old does not mean solved. It means there has been more time for one weak spot to hide.
So let us stop talking about it and watch it happen. Coming up, we walk into a lab login as the admin and dump an entire credentials table with one keyword. Then we write the single line that ends the whole attack. Once you see the bypass with your own eyes, it never leaves you. So let me actually run you through it, because describing this attack does it no justice. Picture a normal login page that asks for a username and a password. Behind that page, a developer wrote a query that checks the database for a matching row, and that is where the whole story turns.
One safety note before any command. Everything here runs in an isolated lab, a deliberately vulnerable app called DVWA on a virtual machine I control. You only ever do this against a system you own or are explicitly authorized to test. We show the mechanics so you can defend against them, never to target anyone.
Picture the developer behind that page, a first-year engineer who just shipped her first login. She wrote the query the obvious way, pasting the username straight into the string, and it worked perfectly in testing. Every example we run looks exactly like the code she shipped, which is why this matters far beyond the lab.
So let me show you the vulnerable query the app builds. Watch how it just pastes the username and password straight into the string. With a normal login of admin and the password hunter 2, the database gets a clean, ordinary sentence. Nothing looks wrong yet. Now watch what one attacker does. I leave the password box empty, and in the username box I type the payload, a single quote, then OR1 equals 1, then 2 dashes. Look at the sentence the database actually receives, and look at what it hands back.
Look at what just happened, piece by piece. The single quote closed the username string early. Then OR1 equals 1 is a condition that is always true for every row in the table. And those 2 dashes start a SQL comment, so the AND password check after it is simply ignored.
The comment trick is worth slowing down on, because the exam tests it directly. In most databases, 2 dashes followed by a space mean ignore the rest of this line. The attacker uses it to throw away the developer's closing quote and the entire AND password clause, so the query stays valid instead of erroring out.
So the database reads a query that says, give me the users where false, or where always true, and forget the password entirely. It hands back the first matching row, which is the admin, and we are logged in as admin having never known the real password.
There is a sneakier cousin the exam likes to slip in. Some apps protect the password field but forget the username field, so attackers target whichever input is concatenated. The lesson is that every single input is a potential injection point, not just the obvious one.
And it is not only login forms. Every input is a door. A search box, a filter option in a web address, a hidden form field, even a cookie the server reads back are all fair game. If untrusted input reaches the query, the injection point exists, whether or not there is a visible text box. One more variant the exam rewards you for knowing is error-based injection. The attacker deliberately breaks the query so the database returns a verbose error message, and that error often leaks the table names, the column names, even fragments of data. The fix there is just as cheap: turn off verbose database errors in production.
And there is one shape that should genuinely scare you, because it is no longer about reading data. It is called a stacked query. On databases that allow it, the attacker closes the first statement with a semicolon, then writes a brand new command right after it, like drop table, or an update that grants themselves an admin role.
That is the line between reading and writing. A union reads what is there, but a stacked query can change or destroy it, even run database commands that touch the operating system. The exam wants you to understand that injection severity ranges from information disclosure all the way to full system compromise, depending on what that database account is allowed to do.
Michael, you have had a hand half raised through that whole demo, so put your question up before I lose you.
Yes, because it is the thing everyone trips on. Why does 1 = 1 log you in as the admin specifically, and not some random user out of the table?
The answer is order. The query returns every row because the condition is always true, and the application simply takes the first row it receives, which is almost always the admin account created when the database was first set up. Bypass the check and you inherit whoever sits at the top of the table.
And that is authentication bypass. The first thing the exam wants you to recognize. The attacker did not crack anything. They rewrote the logic of the query itself. Hold on to that, because once you are inside, you do not have to stop at logging in. Quick, honest ask while we are here. If this has been worth your time so far, hit like, then subscribe and ring the bell. I know everyone asks, but this one is free, and it is how a small channel like this actually grows.
Bypassing the login is loud, but the real prize is the data, and there is one keyword that turns a harmless search box into a window onto the entire database. It is called union, and abusing it is the move that turned MOVEit from an embarrassment into a catastrophe.
Union is normal, legitimate SQL. It glues the rows of a second query onto the rows of the first. An attacker abuses it by adding their own select, pointed at a table the page was never meant to show, like the user credentials table.
But a union only works when both queries have the same number of columns, so first I have to probe the column count. I climb with order by 1, then order by 2, until the page throws an error. The moment it breaks, I know the count, and notice that probing is itself a loud signal sitting in the logs. Now I have my count, so into the product search field I inject a quote to close the string. Then union select username and password from the users table. Then a comment to discard the rest. Watch the credentials appear right inside the product list, where a price was supposed to be.
And notice the passwords came back as hashes, those long strings of hex. That is not the win it looks like. Those are unsalted MD5 hashes, and an attacker feeds them straight into a cracker to recover the plaintext, which is a whole separate failure we cover in the password attacks episode.
Now scale that one injectable field up and you have MOVEit. The attackers did not stop at a credentials table. They reached the files organizations had uploaded to transfer. Employee records, financial data, health files, pulled out one injected query at a time across thousands of servers.
And that is the leap the exam wants you to make. A single injectable field is not a small bug. It is potential access to every row of every table the application can reach. The severity of SQL injection comes from how much it unlocks once it works, not from how hard it is to pull off.
In the real world, nobody does this by hand for long either. There is an automated tool called SQL map that finds the injectable parameter, counts the columns, fingerprints the database, and dumps every table for you. Stick with me on the defender side though, because that automation leaves a very recognizable trail.
It does, and that is the Security Plus angle, the indicator. Watch for a burst of malformed queries, repeated single quotes, and union keywords spiking in your web logs, all from one source in seconds. That pattern is Objective 2.4 territory, the indicators of malicious activity you are trained to spot.
Now the version going around says every injection dumps data this cleanly. That one is only half true. Sometimes the page shows you nothing useful at all, no data, and no error. That does not mean you are safe. It means the attacker switches to blind injection.
There is actually a clean map of these attack families, and it makes the whole landscape click into place. Let me put it up while Erica walks the two main branches.
Start at the top with in-band injection, the data returning side. The data comes back through the same channel you attacked, either inside the results like that union we just ran, or leaking through a database error message. It is fast and noisy. That is the family we just demonstrated. Drop to the other major branch, inference, which the exam calls blind injection. The attacker sees no data on the page at all, only the application's behavior, and reads the database out of that behavior one bit at a time.
And blind splits two ways the exam names directly: Boolean-based, where a true condition changes the page and a false one does not, so you read data one yes or no at a time; and time-based, where you force the database to sleep for a few seconds when the answer is yes.
Make Boolean blind concrete for a second, the attacker asks. Is the first letter of the admin password greater than the letter M? A normal page means yes, a broken page means no, and they narrow it down letter by letter, like a brutal game of 20 questions against the database.
And time-based is the version that works even when the page never changes at all. The attacker injects a command that says, if my guess is correct, wait 10 seconds before answering. A slow response means yes, a fast one means no. It is painfully slow, but it is fully automated and it cannot be stopped by hiding the output.
Here is why this distinction earns its place on the exam, not just in theory. Picture a Tier 1 analyst watching a dashboard at 2 in the morning. A union attack lights her board up with database errors in seconds. A time-based blind attack shows her almost nothing, just one endpoint that is mysteriously slow for hours.
So in-band is the smash and grab, and blind is the patient interrogation. Same root cause, two very different fingerprints in your logs. Keep both in your head because they lead straight into a real argument about how you are supposed to stop this at all. Here is where smart security teams genuinely split, and it matters for the exam and your real job alike. You have just seen how total this attack is. So the question on the table is sharp and practical. You walk into a company already running 1,000 legacy web apps. Where do you spend your effort first? On detecting these attacks or on preventing them at the source? Elena would put a web application firewall in front of everything today. Michael says fix the code or nothing else matters. Elena, make your case.
You cannot rewrite 1,000 apps by Friday, and most of them are vendor products you do not even have the source code for. A web application firewall sits in front of all of them today and blocks the obvious injection patterns the moment they hit. You also get logging and alerting. So when someone tries that union trick, you see it, you triage it, and you respond. Detection buys you time the rewrite never will.
Hold on, Elena. That response speed is not abstract, so put a real clock on it. With MOVEit, how much warning did defenders actually get?
Barely any, and that is exactly my point. The gap between the first exploit and the public advisory was only a few days, but the attackers were already inside thousands of servers. A firewall that flags the attack on day 0 is the difference between an incident and a catastrophe.
Time, sure, but a firewall is a filter, and attackers beat filters for a living. They encode the payload in hex. They split it across 2 parameters. They swap in a comment style the rules never anticipated. A firewall that blocks 1,000 known variations still loses to the one it has never seen, and the attacker only has to win once.
So we leave the front door open for years, waiting on a code fix?
No, the firewall is the seatbelt, not the brakes. Fix the query and the entire class of attack disappears, every variation at once, encoded or not. A parameterized query makes injection structurally impossible, because the input can never become code in the first place.
Michael, before Elena answers that, name the cost of your side honestly. What does fixing every query actually demand from a team?
It demands touching every query in the codebase, which is real work, and it means writing regression tests so a future developer cannot quietly glue a string back in. The legacy modules are exactly the ones nobody wants to open. That is the honest catch, but it is one-time work that ends the problem. Instead of a filter you pay to tune and maintain forever and still lose to.
Both of you are circling the part the standards settle outright, so let me bring in what they actually say. The official objectives and OWASP draw a clear line here, and it favors Michael's frame. A web application firewall is a compensating control, useful but secondary. The primary defense named in Objective 2.3 and by OWASP is parameterized queries, backed by input validation. The firewall reduces risk. The parameterized query removes the vulnerability.
So am I wrong to put a firewall in on day one?
Not at all, and here is the verdict, because you are both partly right. Per OWASP and Objective 2.3, deploy the firewall today as defense in depth. You cannot fix 1,000 apps overnight, so treat it as the temporary shield. But parameterized queries are the cure, so if you only fund one of the two, fund the cure.
Detection buys you time, prevention ends the problem, and a mature program runs both with prevention as the priority. That is the answer to pick when an exam question forces you to choose the single best control. Now let us actually build that cure. We promised one line of code that would have stopped MOVEit and every demo you just watched. It is time to write it. The fix is not a longer blacklist or a smarter filter. It is a completely different way of handing the query to the database.
And there is a tempting wrong turn we have to kill first, because new developers reach for it every single time.
Right. The instinct is to escape the dangerous characters, to find every single quote and put a backslash in front of it. It feels like a fix. It is a leaky one because there is always another encoding or quote style some database quirk lets slip past your rules. Blacklisting bad characters is a game you lose eventually.
And the whole point of the real fix is that you stop playing that game at all. You make the input incapable of ever being read as code, so there is nothing left to filter for.
Here is the mechanism. The vulnerable version glued your input into the query string, so the database parsed input and code together. A parameterized query, also called a prepared statement, sends the query and the data on two separate tracks. The query structure is locked first, then your input is bound in as a pure value.
Here is the analogy that makes it stick. The vulnerable version is like reading a letter out loud and doing whatever it says, so if the letter says ignore your previous instructions, you obey. The parameterized version is a form with labeled boxes. Whatever you write in the name box is treated as a name, no matter what you scribble there.
So let me show you the difference, side by side. Watch the question mark, because that is the placeholder. In the safe version, the username never touches the SQL text at all. It is delivered separately on its own track as pure data.
And here is the beautiful part. Send the exact same attack payload into the safe version, the OR1=1 that broke us wide open earlier. Watch where it goes now, which is absolutely nowhere. The database treats the whole payload as one literal username and looks for a user actually named that exact strange string, quotes, dashes, and all. There is no such user, so the login simply fails. The attack did not get blocked by a filter that might miss the next variation. It got disarmed at the root because the input was never allowed to be code in the first place.
That is the whole episode in one screen. The myth says you stop injection by scrubbing for bad words. Busted. You stop it by making input incapable of ever being code, so the same payload that dumped the table is now just a wrong username.
2 backups belong in your answer for completeness, but know their rank. Input validation, allowing only the characters you expect, is a strong second layer. And least privilege, so the web account cannot read the credentials table even if injection slips through, limits the blast radius. Neither one replaces the parameterized query.
Make least privilege concrete, because the exam loves the consequence. If your web app connects to the database as a near administrator account, an injection reaches every table and can run those stacked commands we saw. If it connects as an account that can only read the product catalog, the very same flaw leaks a price list instead of a credentials table.
The exam also names 2 siblings of the parameterized query that get the same job done. Stored procedures, where the query lives inside the database and you pass in parameters. And modern object relational mappers, the libraries most frameworks ship with, which parameterize for you by default.
One honest caution, because here is how those fail. A stored procedure is only safe if it does not turn around and build dynamic SQL from your input inside itself. People assume the label makes them safe and skip the binding. The technique protects you. The name on the box does not.
Well put, the through line for every method that works is identical. Keep the code and the data on separate channels, always. Whether it is a placeholder, a stored procedure, or an ORM, the input is never allowed to become a command.
And for the exam, watch the exact wording. When a question asks for the most effective control against SQL injection, the answer is parameterized queries or prepared statements. When it asks what to add for defense in depth, that is where input validation and least privilege come in. Knowing which word the question uses is half the battle.
If you forget everything else from today, remember this one sentence. Never build a query by gluing strings together. Bind your inputs as parameters, and an entire family of attacks, the family that cost 93 million people their data, simply stops existing in your code. Let us lock in the one idea that carries the whole exam objective. SQL injection is untrusted input becoming executable code. The same flaw that exposed 93 million people through MOVEit, and a parameterized query ends it by keeping input and code on separate tracks.
Carry these distinctions into the exam. In-band returns data directly, blind infers it from behavior or timing. The primary defense is parameterized queries, with input validation and least privilege as supporting layers, and a web application firewall as a compensating control.
Here is what you walk away with tonight. Open any project you have written that talks to a database, find where a string gets glued into a query, and swap it for a placeholder. In about 30 seconds, you just closed the most exploited web vulnerability in history, and you will recognize this attack instantly the moment a question describes it.
Next time we keep the lab running and go after cross-site scripting. Same theme of untrusted input, but the victim is the browser, and the payload steals a session cookie in front of you. The XSS episode will feel like a sequel you already half understand.
If this made injection finally click, subscribe and stick with the series, because we are building the One Security Plus playlist where you watch every attack happen instead of just reading about it, and the free practice questions to drill this objective live at certs.professorerica.com.
Here is the one we want from you. Have you ever found a SQL injection flaw in real code, your own or someone else's? And what did you do about it? Tell us in the comments.
History keeps the receipts. Read them now and then.
Solid 9, Isabella. I had to rewind a section because I was taking genuine notes. This is Professor Erica. Thanks for watching and signing off.